you so much for coming. So we'll continue talking about security. If you remember from last class, we started talking about the OSI reference model, right? So we said, we started from, on top we start with the application. Then you have transport. And then you have the network. Okay, data link layer and the physical layer, right? So last week I think we spoke about the security at this level, the application level, right? So for example, you have HTTPS, for example, okay, how to apply security at the application level. Today we're going to talk about security at transport layer. So we're going to talk about SSL, SSL plus the TLS, okay, which is a newer version. TLS is a newer version of SSL or upgrade for SSL, right? And this encryption or this, security happens at the transport layer, right? Then next week, maybe next lecture, we'll talk about security at the network layer. So we talk IPsec, right? So you could have security on the three layers. All right. So that's the focus of today's lecture, to talk about security into the transport layer. Okay. So we'll see how is it applied and all of that. So we're gonna discuss the need for security services at the transport layer of the internet model. We discussed the SSL and discussed the TLS, and then we compare SSL to TLS. That's what will be the topic for today. So, as you know, you have the IP protocol on top of it, TCP application layer. So SSL or TLS comes like an additional layer between the TCP and the application layer. So the data coming from the application layer will be secured with SSL before it moves to TCP. So that's exactly what we try to do. So let's take a look at SSL architecture. So SSL is designed to provide security and compression, both security and compression. Compress the data to the data generated from the application layer. So the data generated in here will be secured and compressed with this layer before it goes to the transport layer. Okay, so the services provided are fragmentation. So the data will be fragmented, divided into fragments, compressed. Each fragment will be compressed. It will have message integrity. So we'll try to make sure the message was not changed. Okay, and then we have confidentiality. That means encryption. The data is secret. And then framing. You put everything in the frame. That's the services are provided. So so framing, it means adding a header to the encrypted payload before it's sent. Okay. So that includes a key exchange algorithm. So the key exchange algorithm, because for all of these functions you need to have keys. For example, for confidentiality, you have to have a key, right? So the source has to use a key, and the destination has to use the same key if it's symmetric encryption for the decryption, for example, right? So we have to have a mechanism for key exchange algorithms. It could be null. Okay, that means you're not using confidentiality, for example, because these services, not all of them you need to use with them. Depends on the depth of security that you need. You could pick and choose. We'll see how is that, right? You could pick and choose, right? So, or RSA, we already covered RSA, which is for encryption. RSA is needed for encryption, and you could have an anonymous Diffie-Hellman. So, what does Diffie-Hellman do? No, Diffie-Hellman exchange keys, right? without a third party. So right, Diffie-Hellman you can able to. Then you have ephemeral Diffie-Hellman. Okay, this is for it uses RSA or DSS, and fixed Diffie-Hellman, RSA or DSS, and for TESA, which is used by the Army. We are not going to cover it in this textbook. All right. So one of these algorithms could be used for the key exchange, exchange. All right. So both the client and server need to know the value of the pre-master secret that is used for creating all of this security. All right. So we will have 6 cryptographic secrets, 4 keys, and 2 initialization factors for this process. Okay. Again, for null, both the client and server need to know the value of the pre-master secret. So before they start, they know it. Okay, before they start, they know it. So there is no exchange for that. Or you could have RSA, maybe. Okay, so for null in here, there is no key exchange in this method. So no pre-master secret is established between the client and the server. Both the client and the server need to know the value of the pre-master secret. Before the whole process, they have to know it in advance. By paper exchanging, by phone call, you don't have to exchange it with the system. All right? Then RSA, okay, and you know what's RSA? RSA key exchange server. You know, RSA usually have public and private key, right? So what you do, okay, this is the client and this is the server. So this is the pre-master secret key that both need to share. So what you do, you encrypt it with the server's public key. So you encrypt it with the server, so the client is encrypted with the server's public key. When it goes to the server can read it with its private key. Right? Very simple. Right? We have learned all of that before, right? How to use public and private key easily. All right? You could have anonymous Diffie-Hellman. You know what's Diffie-Hellman? They try to generate a common secret key without a third party. So each one starts with a half of the key and then make key. So the way it starts that the server picks G and B, okay, and G to power S, all right? G and B are shared between the client and the server, but the S is created by the server and C created by the client. Now random number. They choose random number, right? Okay, and they exchange it. So what will be the key? It will be G to the power CS, C from the client and S from the server, mod B. So we learned this technique last lecture, maybe, or the lecture before last lecture, how we are able to share a secret key without having a third party. All right? The only thing you have to know publicly is G and P. And of course, we said, how is it secure? Since the algorithm is there, we said that the S and C are big numbers, huge numbers. So it takes forever to guess them, right? Right? So Diffie-Hellman. All right. So then we said ephemeral Diffie-Hellman key. Okay, what you do in here? So you do signatures, right? So for example, for security, for extra security, that there is no middle. You know, Diffie-Hellman. What's the problem with Diffie-Hellman? Man in the middle, and they have problems. So to make sure it's not compromised. Okay. So to thwart the man in the middle attack, ephemeral Diffie-Hellman key exchange can be used. Each party sends a Diffie-Hellman key signed by the private key. So what you have in here, you have the G, the B, the G is the same thing. However, you sign it with what? We sign it with the private key of the server. Private key. You sign it. I'm sorry, with the public key of the server. When it goes in here, the client can make sure the server signed it using the public key of the server. Same thing in here. You don't send it like this. Before in here we send it plain. and here sent signed by the client. So the client will sign it with his public key, and the server will be able, a private key, and the server will be able to read with his private key. So what's the difference in here? It's the same thing. We created the same master key in here. However, the communication is signed to protect against man in the middle. That's the idea of the signature. So everything will be signed. Clear so far? All right. All right. So, and there is also fixed Diffie-Hellman. All right. So in the fixed Diffie-Hellman, another solution is a fixed Diffie-Hellman method. All entities in the group can prepare fixed Diffie-Hellman parameters like G and B. And this is, you could use authentication, certification authority to exchange these numbers. Okay. Fortese is derived from Italian word fortresses, or fortress, is a registered trademark to the U.S. National Security Agency. It is family of security protocols developed for the Defense Department. This one. So we are not, I mean, this textbook does not cover it, and we are not going to go over it. Alright? So anyways, what we are trying to say here, just to go back, I mean, to be able to achieve some of these services, you have to have a pre-shared or a master key shared, right? Okay? Or not. Alright? So you could do that, null, that there is no shared key, RSA, anonymous Diffie-Hellman, ephemeral Diffie-Hellman, fixed Diffie-Hellman, and Fortese techniques, right? And explain all of them. All right. So when you talk about encryption and decryption algorithms. For encryption and decryption, you're gonna have a key. So how you can encryption algorithms? So for example, if there is no key, there is no encryption. You could use a stream RC4, okay, or block RC2, or block this encryption, or block IDEA, or Fortese. So there's different flavors of these encryptions. All right, I mean, we have studied this, right? And this is kind of a block encryption, not stream encryption. We have studied RC4. It could be stream or block. IDEA, we did not study the details, but there is one encryption called IDEA. Fortese, of course, we did not study it. So, for example, the most common one to us is like this 40 CPC, or this CPC, or 3 this EDC, electronic code, whatever, and CPC, the chaining, the five modes. Remember in the chapter 4 or 5, we said the 5 modes for encryption. So that is for encryption, right? So null, the null category simply defines the lack of an encryption-decryption algorithm. There is no encryption-decryption. We use other services, but no encryption-decryption. Possible. I don't need to have encryption. I don't need to have privacy. All right. The other thing is stream RC. 2 RC algorithms are defined in the stream mode, and there is a block. You know what's the difference between a block and a stream? We explained that, right? So the block encryption, we divide the data into blocks, right? Stream on the fly, so we encrypt them exactly, bit by bit or byte by byte, right? Okay. And there is one RC algorithm is defined in a block mode, and this, for example, all these algorithms are defined as a block mode, like a block mode. IDEA algorithm defined in a block mode, okay, with 128-bit key. Fortese is, I mean, it's one of the techniques, but we don't discuss it in here. All right. So here we're talking about encryption decryption. Encryption decryption to provide what surface? Which surface? Which one? Which one of these decryption provide what surface? Confidentiality. Alright? So we use it for confidentiality. Very good. Just want to make sure you're awake. He is not awake. I think you are not awake. Right? You are not awake yet? Okay. Alright. So let's talk about hash algorithms. Why we need hash? Hash. Why do we need hash?
So we can get the digest.
The grid digest for what?
For the
Message integrity, for example. Message integrity. So before you send the message, you create a hash.
yes.
After you send it, you create another hash. You compare them. If they are the same, then the message is integral. There's no changes, right?
Yes.
Okay? So this is one of the surfaces, right? Anyway, so, and we have learned how many hash algorithms in this book? Many. Alright? So, alright. So remember here we are talking now about a specific protocol, which is Ssl. Right? Ssl, right? So Ssl adopts some of the algorithms from here and here and here. So we're studying about something, real. Right? When I tell you what you want to buy a car, what a color for a car you could have. You could say red, black, brown, green, gray, all a car. But when I tell you Honda 2018 Accord, what colors you have? When you go to the dealer, you'll find 5 colors maybe, right? Not all the colors. They choose, right? Same thing. There are so many algorithms for encryption, decryption, right? But for Ssl, which ones it adopts, right? Which one is used? That's what I'm trying to say. It's like a real product that we use every day. Clear? So hash algorithms for message integrity. So you could have null. I don't need to have hash. I don't need to create digest. MD5 or SHA-1. So basically MD5 and SHA-1. Do you know what SHA-1? Yes. Do you know how it's spelled? Yes, from previous. About MD5? Yes, we studied MD5, right? So now we use it as a block. So for null, the two parties may decline to use an algorithm. In this case, there is no hash function and the message is not authenticated. So we don't care about authenticating the message. Or we could use MD5. The two parties may choose MD5 as the hash algorithm. In this case, 128-bit MD5 hash algorithm is used. Not very secure, it's only 128-bit. Remember what we said when we tried to analyze these algorithms before, that we said, we should not use less than 512 digest, hash. So SHA-1, okay, also the two parties may choose SHA as the hash algorithm. In this case, 160-bit SHA-1 hash algorithm is used. Okay, so there is two options. About Cipher suite, so the combination of key exchange hash and encryption algorithm defines a Cipher suite for each Ssl session. All right. So there is a session, there is a Cipher suite. Okay, which one they're gonna use? So for example, in here it says Ssl. Okay, it's gonna use RSA with this CPC mode, chaining mode, and for hashing it will use SHA. All right. So both parties, the sender and receiver, has to agree on this suite, because if you do at the sender with SHA, you have to do it again with SHA at the receiver. So they have to agree on this. So each suite starts with the term Ssl followed by the key exchange algorithm. So what is a key exchange algorithm? Okay, the word with separates the exchange algorithm with the encryption and the hash algorithm, as you see there. All right. Oh, here. So in here, this is Ssl suites. So there's so many suites, prefix suites. Just they have to agree on that. So if you take a look at the first one, in the first one, there is no key exchange, there is no encryption, there is no hash, there is nothing. While if you look at the last one, for example, it's using for Ssl for the key exchange, it's using RC4 for encryption, and using SHA-1 for the hash. So this is sweet. It has to be agreed upon between the sender and the receiver. By the way, in our emails, I mean, if you go to the configuration, we use Ssl and Tls, right?
Yeah.
That's how it's secure, right? So that's all right. So this is clear, right? So we said the Ssl provides two things. What are they? Security and compression. You gain the gift. I'm not sure what the gift they're gonna give you. Okay. All right. So just give him a picture. I mean, that everybody knows he's, you know, he's awake. All right. All right. So compression, right? Security. And security, how many surfaces we have? So in terms of security, how many surfaces we have? One, two, three, four,
5.
five. So security is 5 surfaces, and you have compression. So for compression is optional in Ssl version 3. No specific compression algorithm is defined for Ssl version 3. Therefore, the default compression method is null. The default, but all compression always increasing the security because the data will be completely changed when you compress them. You agree? Okay. So, and it will reduce the amount of data, but you know, you don't have to use it. So now we're gonna come to the parameter exchange. So the cryptographic parameter generation, okay. So you're gonna. What are the parameters? There are six secrets that the sender and receiver has to exchange. 6 parameters have to exchange, right? 4 keys and 2 IVs. You know what's IV? Initialization vector. In many algorithms that you need to have IV starting value. We call it starting value or IV or initialize. So these needs to be exchanged, right? So to achieve message integrity and confidentiality, Ssl needs 6 cryptographic secrets, 4 keys and 2 IVs. The client needs 1 key for message authentication, for HMAC. The client needs for message authentication, right? And 1 key for encryption. When you do encryption, you have to have a key. And 1 IV for block encryption. If you remember from the block encryption, we start with the IV, right? Go back to chapter, I think, 4 or 5 or 8, when we have the mode, right? How to connect the blocks, right? Remember that? So we have the IVs. Okay, the server needs the same Ssl requires that the keys are one direction by different from these for this other direction. All right. So the client and the server exchange starts by exchanging 2 random keys. Okay, numbers is created, and so in here. So that's what it is. So you have in here, for example, PM, which is a pre-master secret, CR, the client random number, and SR, the server random number, and you have a value, okay, and SHA-1, then another, you create a hash, you add the pre-master secret in here, you do another hash in D5, and you create the first hash. The same process here, same process here. So you're gonna have 48-bit, this is the master secret. So how you create the master secret between the sender and the receiver. You start with the master secret. You have to have 1 master secret. Okay? So master secret starts, so you know, calculating the master secret starts by free process to generate 48 bytes. 48 bytes. Alright? Again, the A and the BB and CC preset. Preset. They are always there. PM, what is PM? The pre-master secret used. And then the CR is the client random number and the server client number. Group, second group, third group. All of them, you do SHA-1 for them. You're gonna create a hash. Just to increase the security, we do another hash. Using what? MD5. But after we add the pre-master secret again. Okay? You know the blending and bind, okay? Well, that's the method. That's how they designed it. Alright? So at the end you're gonna have 48 bytes, that's the master key. Right? So calculation of the key material from master key. Alright? So then from the master key that we generated in here, the master key that we generated in here, you need to, so M is the master key that generated, you can generate other keys from it. Okay? So SR the server random number, CR the client number. Again, A, B, 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 as much as you want. Okay? And you do the SHA-1, okay, hash, the M, the MD5, then you create the key material. So the parameters are generated using the following procedure. Number one, the client and the server exchange two random numbers. They have to exchange two random numbers. It's server random and the client random. Okay? One is created by the client and the other created by the server. Okay? Okay. Number two, the client and server exchange one pre-master secret. One pre-master secret using one of the key exchange algorithms like we studied before. Alright? Number three, a 48-byte master secret in here is created from the pre-master secret by applying two hash functions, SHA-1 and MD5 as shown. So from this process we were able to generate the master secret. Alright? So basically they have to exchange the client random number, the server client number, and the pre-master. From that you're gonna generate the master key. From the master key you're gonna generate everything else after that. Alright? Number four, the master secret, which is generated in here, is used to create variable length key material by applying the same set of hash functions and prepending with different constants as shown in this figure in here. Alright? Then after that, okay, 6 different keys are exchanged from key material. Okay, then after that you're gonna create 6 different keys. So extraction of cryptographic secrets from the key material. You have authentication key, which is for authentication. You have encryption key, and you have the IV initialization vector. So this is the key materials created in here. So client authentication key, server authentication key, client encryption key, server encryption key, client IV, server IV. These are the 6 values that need to be exchanged or generated for all the communication. Alright? Now, there is something called session and connection. Alright? Session and connection. So these values are used for one session. But the session could have multiple connections. Okay? So usually when you have an email, for example, when you connect, for example, to a server, you don't have to connect multiple times. Every time you send an email, you connect again, right? You create the session and you could send many emails, right? Many emails during that connection, right? So in a session, one party has the role of a client and other role as a server. Server, like mail, client mail server, okay? When the client needs to communicate with the server, when you need to check your email from your computer, you log into UB mail server, right? Server and the client. So what you are creating? Session, all right? Both parties have equal roles. They are so in the session is a client server connection. In the connection, both parties are equal roles. They are peers. It's not a client server, right? So session could have multiple. One session could have multiple connections. Alright, a session can consist of many connections. A session can be suspended and resume again. Alright. So what will happen, let's take a picture in here, yes, a session and a connection. So you have in here a client and the server. So this is a session state to establish a session between a client and server. Session is between a client and server, it's a client-server application. Once you establish the session, you could have how many connections? Many connections. So you have connection, another connection, multiple connections. And the connection is like peer-to-peer. It's not like you know, it's not the client server. All right. All right. So what is session state? You know, a session is defined by a session state, a set of parameters. Set of parameters established between the server and the client. As you see in here. So the parameter, for example, session ID, peer certificate, compression method, Cipher suite, master secret, is resumable. Is, you know, can you suspend it and resume it or not? You have to close it. Okay. So these are the parameters for each session. It's like description, attribute for a session. So let's take one for the session ID. So it's a server chosen 8-bit number defines a session. Okay, so server could have multiple sessions with multiple clients. For each session, you could have a serial number, kind of, or ID number. Okay, peer certificate, a certification of type X509 version 3. We studied that last time, right? Certificates, right? This parameter may be empty or full. Right? Compression method. What kind of compression? Is there a compression or there is no compression method, etc., etc. So session state, what does state means? Memory or a status. Alright? So HTTP, for example, is it stateful or stateless? Huh? Stateless, right? Stateless, yeah. There's no memory to remember the connection. So to make it stateful, what we added cookies later, right? Right? Cookies to remember things, right? Okay, same thing is a state. So state means a memory, you know, it's between the session, the both party had to remember protocols in general, or the communication protocols in general, either stateful or stateless. Memorize the state or does not memorize the state or parameters, right? Now for the connection state, okay, this is for connection state. The connection is defined by a connection state, a set of parameters established between two peers, as you see in here, between two peers, shows the list parameters for connection state. Ssl uses two attributes to distinguish cryptographic secrets, write and read. So there is a write state and read state. Alright? And these are the parameters. So for example, you have server and the client random number, server write MAC secret, secret write MAC secret, server write secret, and so on and so forth. So there's different parameters that are used. Okay, so the client and the server has 6 different cryptographic secrets: 3 read secrets and 3 write secrets. The read secrets for the client are the same as the write secrets for the server, and vice versa. Alright? Alright? So what you have learned so far, SSL, it happens in the transport layer. There is 4 keys and 2 IVs needs to be shared. Okay? There is certain protocols for encryption, decryption needs to be used. There is something called a session. Session is kind of server.
Peer.
Connection is peers.
Yeah,
Connection is peers. but session is like client server, server connection. There's a state. State means parameters need to be known by that, and there is a connection which is a peer-to-peer. So one session could have many connections, and the session could be resumable or not resumable or not resumable, right? That's what we learned so far, right? Yes.
Okay, yes. If there is no memory, how can you resume the session?
If there is no memory,
Yeah.
we have to have the memory, otherwise you can't establish the session. So these parameters, we try to establish them initially, okay, by sharing the random number from the client, random number from the server, and the pre-master. Then we create the material key, and from the material key we generate all the keys. Okay? So you have to have memory, otherwise you can't establish that connection. All right, four protocols. Okay, used. Okay, four protocols used. So we have discussed the idea of Ssl without showing how Ssl accomplishes its task. Ssl defines four protocols in two layers, as shown in figure here. So you have in here four protocols. So this is the transport layer, this is the application layer, and in between them we're going to have four protocols. The first protocol is Handshake Protocol. The second one is Change Cipher Spec Protocol, Alert Protocol, and the Record Protocol that moves the data, Record Protocol. So four, all right. So you could go from the application layer directly to the Record Protocol, and these three goes to Recorded Protocol, and then to transport. So you see four paths. So we need to take a look at these, how they work, what they do. The four protocols. Okay? What they do, right? So we have discussed the idea of Ssl without showing how Ssl accomplishes this, right? So, alright. So the first one is the Handshake Protocol. The Handshake Protocol. So you have a client and a server in here. Phase 1, establish security capabilities. In phase 2, server authentication and key exchange. So you're gonna have server authentication. Okay, the client will authenticate to the server and the key exchange. In phase 3, client authentication and key exchange. Remember that we said authentication has to be mutual, right? Client needs to be authenticated to the server, and the server needs to be authenticated to client, right? Then after that, finalizing the Handshake Protocol. So how many phases we have in here? 4 phases. And that's all for the Handshake Protocol. Again, you establish security capabilities, you authenticate the server, you authenticate the client, and you finalize the handshake. So for phase 1, establishing security capabilities, okay, how it will happen in here. So it's in phase 1, what will happen is the client will send a message called the client hello. Client hello. Hello. I mean, if I need to establish a communication with you, how I start? Hello, right? Same thing in here, we say client hello. So in the client hello, you're gonna send the version of the Ssl you're using, client random number, then session ID, Cipher suite. Cipher suite, you know. Remember the suites we looked at? Okay, you have to agree, okay? And then the compression method. Is there a compression? There is no compression. Okay, so it's a hello. So it's like, hello, I would like to communicate with you by phone. So now I send you hello, and I told you the suite is by phone, for example. In here, the client send and it tells how we want to communicate. Then the server responds with hello, the version, agrees with it, server random number, so this client server random number, session ID, selected cipher set, because he sent like a suite, he selected, and then selected compression method, right? Maybe he will send options, the client send options. Let's do compression this or this. Then the server will confirm with one of them. At the end, yes.
Yeah, the compression method, is it compulsory that it must be encapsulated in the initial connection, that's from the client to the server?
In here we're trying to, in here they're trying to know what kind of compression. Is it zip? Is it, there's different techniques for compression. So in here the client compression method tells the server, can we use zip? Can we use RAR? Can we use what kind of techniques? Then the server responds, oh, let's use only zip.
Sorry, like, let me make a scenario now. The client now is the computer. The server is a printer. The computer wants to print something from the server. Is there any sort of compression in that connection, in the interaction between the computer and the server?
We are talking about data exchange, right?
Yeah.
Block of data. So this data can be compressed or not compressed. Printer has nothing to do with this, because a printer, there's nothing. A printer is a client. There's a printer server and the client, right?
Yeah.
Okay. So if you need to send the data to the printer, okay, do you compress it? Usually not. But let's talk about mail server. Okay, you need to exchange like 1 giga file. Do you need to compress it, or you want to send it without compression? Who gonna agree on that? The server and the client. Because if they don't agree and the client send it compressed, the server will not be able to read it, right? So the server needs to know the file received is compressed. That's number one, and what kind of compression used, what kind of algorithm, right? So the client in here tells the server, hello, I could use this method or this method or this method for compression. The server responds with one, selects one, use only this. So now they have an agreement what kind of compression they're gonna use, if at all. So maybe one of the options in here, null, no compression. The server says the null, no compression, not use the compression. Did I answer your question?
Yeah.
All right. So that's phase one. So after phase one, the client and server know the following: the version of SSL, because there's different versions of SSL, so they have to agree in the version, right? The algorithms for key exchange, message authentication, encryption. So for encryption, what we are using together? DES, triple DES, something else? We have to agree, right? For authentication, are you using SHA-1? Are you using MD5? They have to agree. Then the compression method, they have to agree in compression method. And then the two random numbers for the key generation. Okay, they have to agree in the random number for key generation. In the phase two, handshake protocol, so what you have in here, the server sends a certificate, a chain of certificates, and server key exchange, server public key, it will send it, certified, and certificate request, it will send list of acceptable certificates, list of acceptable authorities. And the server hello is done, it will send no comments, for that. So in the phase two, trying to send the key exchange and authentication. The key exchange, the server key exchange, and authentication. So after phase two, the server is authenticated to the client, and the client knows the public key of the server if required. Then you have, okay, so for 4 cases in phase two, in here, as you see, so using RSA, or using anonymous Diffie-Hellman, or ephemeral Diffie-Hellman, or fixed Diffie-Hellman. Let's take a look at one of them. Okay, so the server will send RSA encryption certificate, okay, to the client, and then no server key exchange. So send the data encrypted. In here, what does it do? No certification, but it will send the GEP, GOS directly to the with certification to the client. Okay, and so for ephemeral and for fixed, right? Anyways, so in phase 2 we exchange the key and the server get authenticated to the client and the client get authenticated to the server. So in phase 3, okay, what we do in phase 3, we do client key exchange and authentication. So the client sends the keys and the public key and the hash code to prove the certificate. So in here, the client gets authenticated to the server. So after phase 3, the client is authenticated for the server. Both the client and the server know the pre-master key. So by phase 3, they know they are authenticated, and they know the master key. They know the pre-master key. All right. In the last phase, phase 5, phase 4. I'm sorry. Phase 4, you do finalizing and finishing. Okay. So it will change cipher space value, MD5 hash and SHA hash to be sent, and then it will send the change cipher spec value, MD5 hash and SHA. So after phase 5, the client and server are ready to exchange data. So it goes through 4 phases to exchange all the keys. Remember what you are trying to do at the beginning? Exchange the keys. Then we start playing with the data. We use this data onto the data. This keys and IVs and so there is 4 keys and 2 IVs and compression. There is compression. Then we start playing with the data, applying it to the data. Right? So the second protocol is change Cipher Spec protocol. Let me remind you what I'm talking about. So we finished the handshake protocol, right? How many phases it has?
4.
4. Now we're gonna go to where? Change Cipher Spec protocol. Okay? Here. So what we are doing in the change Cipher Spec protocol, so basically we have seen that negotiation of the cyber suite and the generation of cryptographic secrets are formed gradually during the handshake protocol. So during the handshake protocol, everything was done gradually, right? The question now, when can the 2 parties use these parameter secrets after the exchange? When they can use it? SSL mandates that the parties cannot use these parameters or secrets until they have sent or received a special message. So now after we exchange all these parameters, we cannot use them. We can use them only after a special message is sent, which is the change Cipher Spec message. Change Cipher. So after this message is sent, now you can use these parameters. I don't know why. Okay? Which is exchanged during the handshake protocol and defined in the change spec protocol. The reason is that the issue is not just sending or receiving a message. The sender and the receiver need 2 states, not 1. One state is the pending state, keeps track of the parameters and secrets. The other state is the active state. And remember, a state is the memory where you save these parameters. That's what's a state. So there's 2 states, active and pending. Active and pending. So the active state holds parameters and secrets used by the record protocol, okay, and for encryption decryption. Okay. So basically in here what you have two states. You have memory. It's like you have active and pending. So this is a client server. W write, sending, read, reading, receiving. At the very beginning, okay, at the beginning everything at the client is in the pending. And everything at here is in the server and the pending. Before you be able to use these parameters, and the parameters again is the Cipher, the MAC, the Cipher key, the MAC key, the IV, okay, whatever the values, who cares? We cannot use them until you receive the change Cipher spec. Then after that, the client finishes message can be signed and encrypted by the client and verified and decrypted by the server. So this is at the write, and this is for reading. This is for reading and writing, right? Then after you finish the whole thing, after you finish the process, everything will be active, okay? And so the state or the values keep changing. Before we start using them, we have to move them from the pending to active, and for that we have to send this message. That's how it's designed. All right. The last thing is alert protocol. What's alert protocol? To send alerts. So where is alert protocol? Let me go back. Here. Alert protocol. Small protocol in here. Okay. By the way, I understand it will be a little bit confusing. So you have to read it in the book. You have to go in sequence. Okay. And that's the maximum I can do to explain it in here. A lot of data, a lot of information. You need to go back and forth to be able to understand it. Okay, but at least now you have an idea. When you go over it in the book, you'll be able to understand it. Okay, so the alert protocol in here. So there's a lot of alerts. So you have the value, the description, and the meaning. So for example, I cannot read it in here very well. So for example, 0 is close notified. Sender will not send any more messages. What does it mean, right? And so on and so forth. So there is a problem levels, could be warning or it could be fatal. Warning is a warning. Fatal is like it could kill the whole transmission, right? Then we come finally to the record protocol. Where is the record protocol? Is the protocol number 4, which is in the bottom, right? What does it do, the record protocol? It carries the message from the upper layer, which is the Handshake Protocol, the change Cipher Spec Protocol, the alert protocol, and the application layers. Let me go back. There is nothing like seeing it. So what this do? Carry the message from where? Either from here, or from here, or from here, or from the application layer to where? To the transport layer. Okay?
Does it store any kind of data?
Huh?
Does the record layer store any? The record protocol, does it store data?
Of course, it's like forming the whole message received from the upper layers. We'll see it in a second. Okay. All right. The message is fragmented and optionally compressed. So in the record layer, it could be fragment compressed. A MAC is added to the compressed message using the negotiated hash algorithm. The compressed fragment and the MAC are encrypted using the negotiated message. So what will happen here? So this is the payload from the upper layer protocol. It will be fragmented. What does it divided into fragments? So fragment 1, fragment 2, 3, 12. Then it will be compressed. So the payload will be divided into fragments. Okay, then will be compressed, right? And then the write MAC secret, you're gonna take the compress, create a hash, and you add it as a MAC in here. This is for what? For message integrity, for authentication, right? So you take the compressed, you create a hash, okay? You create a hash out of it and you add it in here. What is the MAC in here? The digest. Not digest. What is MAC address? It's a digest. Okay? It's the digest. Alright? Digest. But this digest generated by a key. So it's a keyed digest. Right? So we have the compressed data with the MAC. Then what you're gonna do in here? Encryption for everything. Right? Then you send it. Then this is the encrypted fragment. Right? And you put the SSL payload with the header. Okay? The header. And this is the encryption. That's how encryption happens. The protocol version length. And this is the compressed fragment. Where's the compressed fragment in here? Okay? And the MAC. You send the MAC. Where is the MAC? This is the MAC. So this in here, it's in here. Okay? It's in here. So this is a compressed fragment. The MAC, that's the MAC, depends on the size. And then you have the protocol, the version, the length. And this, all of this in here will be encrypted except the header. Will be encrypted except the header. Why we don't encrypt the header? Because header has the map. So when it moves from one hop to hop, somebody needs to read the map to direct that. Okay, so you don't encrypt it, right? So that's a processing done by the record protocol. All right. So the way you calculate the MAC, where is the MAC? Here. The way you calculate the MAC, so you're gonna have the MAC write secret. You add a band, sequence number, compressed type, compressed length, and compressed fragment. All of them you add them together, and negotiated hash algorithm depends on the hash, right? It will be negotiated. There's two options or three options. What are the three options? Null, MD5, and SHA-1. Null is out, right? And then you take all of the data, you create a hash, still the MAC write secret, the BAT2. All of them comes in negotiated hash algorithm, and then you do the MAC. So that's how is MAC created. It's like complex. Okay, so just you have to know how is it. Okay. So so the next session talks about SSL message formats. SSL message format. All right. I will leave it for you to go over the SSL message format. I will not cover it. It's the how is the message is formatted. So you have to look at the message how it's formatted. If you go through it, you will be able to know it very well. So I'll keep it for you to go over it. I don't think it's very tough for you to understand. Okay, but I would like to mention about the transport layer security TLS. So we're talking about SSL. The TLS, the transport layer security protocol, is a standard version of the SSL protocol. The two are very similar with slight differences. So they are similar with slight differences. So in the versions, for example, the first difference is the version number, a major and the minor. The current version of SSL is 3.0. That's the current one. The current version of TLS is 1.0. So in other words, SSL version 3, it equals to TLS version 1. TLS came after. Okay? Another minor difference between SSL and TLS is the lack of support for TISA method. For TISA is in SSL, it's not supported by TLS. TLS does not support for TISA for key exchange or for encryption. Alright? Now these are the suites, different suites. Remember we looked at the suites in SL. These are the different suites supported by TLS. Alright? Data expansion function, it works a little bit different. So it starts with the seed, HMAC, with the secret. Okay? Anyways, so that's how expanded secret will be done. It's a little bit different. Okay? We already studied SSL. This is like doing it in a little bit different way. Okay, the blender is a little bit different. Just you have to take a look at the key material generation, a little bit different. Okay, alert protocol SSL supports all the alerts defined in SSL except for no certificate. TLS also adds some new ones to the list. So same alert protocol, this little bit bigger, there's more alerts, right? The handshake protocol also is a little bit different, just you need to just take a look how it works. I already explained SSL. I mean, understanding SSL, if you understand SSL, it's very easy to understand TLS. It's the same concept, just like tweaks and changes in here to make it more secure, right? So SSL and TLS are applications or security mechanisms used where? In which layer? In transport layer. And by the way, if you go for your Outlook Express, you go to the configuration, you see that you are using SSL and TLS.
Yes.
It's used everywhere. Okay, in the transport layer. In HTML, for example, when you use HTTPS, for example, it's used there. We could talk more about it. The most important thing for me is the concept, the idea of it. Then next week we'll talk about the last security, which is Ipsec, which happens in the network layer. Okay, network layer, and it's a little bit different because this transport layer is end-to-end security. End-to-end security. So it gets secured at the one end and removed out of the box at the other end. However, in the IP packet, it will be like host to router, router to router, or router to host. It's not end to end. It's device to device. We'll talk more about it next week. All right, next class. I'm sorry. Thank you.
Thank you, sir.